Hey there, welcome back to Intro to Cognitive Science. So, today we're going to talk about mental image representation. This is an important way to think about the way that we process information. Last time we talked about language, right? The last two times we've talked in depth about language, right? We're talking about automated systems, natural language processing, Sherdlu, how it's able to take strings of text, strings of words from the world as that are already symbols, and make use of them, right? But there are other ways to represent information that isn't strictly language, strictly symbolic. So, mental information. We're still winding our way towards being able to talk about the brain as a system of information processing. We've talked about chunking, so how some amount of information can be grouped and stored sort of more efficiently than just one disconnected piece at a time. So, like phone numbers, right? They're easier to map because they have this standard structure and we can sort of break them up, right? We've also talked about language, which has all these rules and structures that we can transform language, we can process language, we can gather the semantics of language from the way that the waveforms hit us, and we convert them into words that we then make sense of, all that. So far we've talked about all of this more symbolic information. Words in language are symbols, right? They are abstract. A word, the word word I throw at you, that you read on the screen here, that you hear me say, is meaningless garbage to an animal, right? It doesn't have an intrinsic meaning. We have given it a meaning. We have given it stands in place for some concept that we're trying to use as we, live this mental life, right? And this is also, these are quite easy to store in bits of information, right? In the computer world, we've talked about how, every letter on this screen is probably stored in about 32 bits. It might be 64 at this point, depending on the way that the different processors work. But Unicode is typically 32. So to represent the word words, that would be 1, 2, 3, 4, 5 letters. 5 times 32. Ugh, don't make me do the math. 150, 170-ish. No, 160-ish. So about 160 bits captures the word words. Okay, great. So what does that mean? What that's getting at is that we're talking about things that can be stored in relatively small amounts of very specific, rigid information. And we talked about how our various channels seem to have some kind of bit capacity, somewhere in that magic number 7 realm, the 2.5 bits of information in those channels. I know that the idea of a half a bit is a little bit confusing, but we'll just leave it there. It's tough to explain that one. So let's look back at the general idea of information processing for brains. Turing was trying to do a lot of formal languages, proofs, logic, the very stuffiest of information, right? Executing instructions, one symbol moving at a time, even if it's just ones and zeros. But there's a different kind of breed of information that we're leaving on the table when we talk exclusively about all this, like, symbol manipulation stuff. So what about close your eyes? I mean it. Try it. I know it's a video and I can't monitor you, but try it. Close your eyes. Imagine the last meal you ate. What did it look like? Well, how did you plate it? Right? Was it just in a box? Yeah, a lot of us eat out of just little boxes, right? Did you unwrap it? What was there? How did it taste? Did it smell good? What did it look like? What colors do you see when you think about this meal that you ate? the experience of your last meal that you've eaten is in there somewhere. And we'll talk if you're struggling to summon some of these little details, don't worry about it. We'll talk about that later. But the idea is, this is information, and you had this rich experience of it. You remember the shape of the bun of the burger you ate, or the color of the vegetables, right? Some of this stuff, it's in there. It's information, but it's not necessarily easily captured by a simple symbol. Okay, keep your eyes closed. You may have opened them by now. Close them again. Imagine an elephant. Now turn it pink. Interesting. Again, some of you may struggle with this. That's okay. We'll talk about that. But you just had an internal experience of editing this information. Normal elephant, right? Of course. We all know elephant, right? Big gray thing with big floppy ears, has a long nose, it does stuff with it. It's prehensile. It's pretty neat. They're huge. And then I made you make its skin turn pink. That's interesting. You not only you've conjured something that doesn't exist in the world too. Your imagination is at play. Again, you may not be able to experience this very easily. It may be a little bit more faded for you. That's okay. The ideas, though, are that this is all still information. It's just non-symbolic information. Open your eyes. You're good. You're good. So, non-symbolic information. Images aren't as easily deconstructed, for example. There's no grammatical rules. There's not even really a clear basic unit, right? If you look at the moon at night, it's taking up a very small amount of your visual space, of your retina, but there's an incredible amount of detail there. What's the basic unit of the information that's reaching you here? Now, we could just say photons, right? But that's tough. I don't think that our eyeballs are processing every single photon in a meaningful way. So, how do we achieve this? What are we doing? How are we keeping track of mental images? Like when I had you imagine the elephant, it kind of took up some space somewhere in your brain, right? You could kind of see it. And again, different levels, but some of you may have very clearly seen an elephant. Some of you may have sort of only dimly seen one, but you still had a representation internally that you could access. What the heck is that? That's wild. We don't think about this in terms of it being a crazy thing that we can do, but we can do it. So, if we're thinking about the brain as an information processing system, how do we do this? How do we keep track of mental images? And that has to do with representation. So, an abstract concept. The idea of representations are generally quite abstract. How does an image get encoded into the neural structures of the brain? So there's a few things here. A few things that would be required, right? It needs to somehow resemble the original thing, right? To imagine a pink elephant, there must be something stored sort of that at least corresponds to each part of its body, right? It could be very finely detailed, potentially, or it could be a little bit more abstract, sort of a conceptual map of, well, I know feet come below joints. I know joints are attached to the hips, to the torso. I don't know if you would call an elephant's chest area a torso, but whatever. So, yeah, how might we actually represent in our minds, in our space, in our mental image, a pink elephant? There's a spectrum here. You could have a very vivid, high resemblance representation. You could have a little bit simplified, lower resemblance representation, or you could have just a fully abstract map of just related ideas, right? The ears and the head are connected to each other. The tail is attached to the body, that kind of stuff. And they're all pink, of course. So these are all valid. These are all valid representations. You may have never even seen a thing before, but if you can still know things about it, and you can still use your internal representation of that thing to good effect. So representations, they are abstract. They are not analog. They are not sort of an exact copy of anything that you've seen, no matter what you're doing in your brain, no matter how clear your memory is of some pink elephant, right? It's still a reduced form. A representation is always sort of reduced. It still has to fit inside your neurons, right? Neurons are not magic. They can only fire so often, they can only transmit so much information, and there's only so many of them in your head. So it's whatever we're doing, it is still a reduced form. We can also connect our symbols, sort of the higher level stuff we've been talking about so far, like language, right? We can connect those to the representations, right? In the elephant map, we can label each part of the elephant as a sort of distinct thing. We can still consider the tail as a tail, but also connected to the elephant's butt, right? It's still part of the animal, right? So we have a mapping, we have floating symbolic ideas above it, but we can also connect it to this more abstract, more representational, or more, sorry, less symbolic and more non-symbolic representation. So, and also another tidbit about this is that you don't need a whole lot of symbols to recall these more diffuse representations, right? I can say the word elephant, the very singular abstract symbol, and it can summon for you an entire host of non-symbolic information about elephants. Maybe the last time you saw one, right? An image, a mental picture of it. Before we go on, let's talk a little bit about computers. So they are always kind of on the side here. This is cognitive science. We're talking about all kinds of computing and information processing and all this. How the heck do computers achieve this? So they handle all of this by way of cataloging light in an array of values that we know of as pixels. So whatever you're using right now, whatever you're using to watch this, it is right now converting stored information into thousands of tiny little specks of light. Have you ever heard 1080p? That means 1920 pixels by 1080 pixels. Multiply that out, you get however many million, right? Close to 2 million pixels. It doesn't look like individual single values of light, but that's how they're stored. That's how it's doing it. It's saying, hey, this pixel in the very upper left corner needs to be blasting out all 3 colors that it knows how to blast out in the brightest capacity they can to create white light. Whereas one of the pixels inside, say, on, in the title here, in the letter O, it's going to say, hey, everybody shut off so that you're black, right? So the way it's doing this is it's storing a numerical value of how bright each pixel should be, so that when all of these pixels come together, they create an image that you can use and make sense of, right? So let's ground this a little better. Here's a breakdown. This is an image of Wikipedia. Yes, that is kind of what it looks like. A little bit darkened, but if you were to open Wikipedia on your screen right now, this is how these lights are being instructed to turn on or off. Some numerical value is saying, hey, little tiny red light, you need to be very bright. Little tiny blue light, be less bright. If you get red and green very bright, but blue is very dark, that turns into yellow. So with modern cameras and modern digital displays, this is kind of an easy transformation. I just take all the light, dump it into a file, and that's how a photo is stored. Any photo you have on your phone was just a camera sensor coming out, looking at the world and saying, I'm going to, for 2 million different little specks on my sensor, record how bright each of these lights should be. That is an internal representation for a computer to make sense of this very non-symbolic information in such a way that you're able to use it. It's able to reproduce it for you. It's able to show you that photo you took last weekend. So, mental pixels? Not exactly. We are not necessarily storing pixels, right? Because we're also not fully recalling every single atomic, photonic detail of every picture we've ever seen. That's not how we do it. We can't reproduce these perfect visual replicas. We can do, some of us do it better than others, and some of us have struggled to do it almost at all. But these are, the idea is down to, in concept, in theory, it's the same basic idea. We are holding some kind of internal version of the visual information in the world that we use. Another thing to think about here is the etymology of the word image. The word image is not about photography. It's about imagining. It's about holding something in image in your brain or in concept or wherever. So a photograph achieves this, but the way it does it is it encodes the image that it's trying to give to your imagination. It's stored and transmitted by way of some, dots on ink. I guess a photograph is technically not ink. It's sort of more of a chemical reaction based on whatever. But you take in the light that bounces off of the photograph and you convert it to a relevant concept. That's my dad's face. You can see on the photo, right? So, how do we do this? This is, of course, where we have to go with all these. We have to ask questions about, how is this possible? What are the mechanics? How does our system use this kind of information? What does it require to do it? And we, as always, we start at the edges. We say, well, what are some limitations? It's possible. It's clear that we're able to do some kind of mental imagery tasks, but are there limits? Are there ways that we can succeed at this and fail at this? So, if we're trying to think of the brain as an information processor, the question is, how do we process imagery? How do we change it, manipulate it, analyze it, and then talk about it, right? You can summon up an image and then talk about that pink elephant that you're creating on the fly. So, we do science to it. We can have people do mental imagery tasks, and then we can see how those tasks can be impaired or improved under different circumstances. This is a good baseline, right? Obviously, we have some proficiency with mental imagery, but can we fiddle with that? Can we interfere with that? What kinds of things do and don't interfere with that? So, Brooks, 1968, the F test. Okay. I'm showing you an F here, but here's the idea. You imagine the letter F. Your job is to mentally trace along it from the bottom left corner, along the F. And whenever you hit a corner, the question that you must answer at each corner is this corner on a top edge? So as in, is this an internal F? Is there a piece of F line above me? Or am I at the top of an F line? So, once again, do it. Okay. I'm starting at the bottom left of the F. I'll go up until I hit the top. Okay, there's nothing to stop me. There's a corner there. Yes, this is on the top. Okay, I'll keep going. Move to the right. I hit the top right corner. Yes, I am on the top corner now. I'll go down. Okay, now I'm not on a top corner. I'm on a bottom corner because I'm on the bottom of this particular plank of the F. Okay, great. So now I'll go left. I hit the internal corner. Still a no because I'm not on the top of this. I'm in the sort of the elbow of the top of the F. Go down. I hit another corner. I am on the top again because we are now on sort of the bar of the F. Go right. Still on the top. Go down on the bottom. Go left on the bottom still. Go down again on the bottom. Go left. I'm back where we started, and that's still a no. That's still a bottom. Okay. I just did the whole thing with you, but hopefully you thought about how I don't know the answers to these things. This is a stupid test. I would never do this in my real life. This is a very abstract thing, but I am able to do it without looking at an F. I'm able to summon some internal version of an F to use for this task. Okay, cool. So that's the baseline. Everyone can perform this to some extent. You might not be as good as your neighbor at it, but you can do something, right? So the baseline is, how well do you do in this test? And here's the experimental manipulation that makes this a scientific study and not just an interesting survey. And that is, there's two different ways. They can ask you to answer verbally, or they can ask you to look at and point to the word yes or no. So either, as I did before, I was just saying it out loud verbally. They can also have you point to one of two answers to give the yes or the no. So what's the issue here? What can we expect? Well, I'm spoiling it on this slide, but when you have to use vision to answer, you do worse. Both your reaction time and your accuracy fall off. Why? What on earth? Why is that possible? That seems so trivial. When I described to you that you could either answer verbally or answer by pointing, I'm sure you said, okay, who cares? But the fact is, pointing screws you up. The F study is illustrating that when you use mental imagery to imagine the F, to make use of this internal representation of the F, you're drawing on some of the same resources that using actual vision to do the task is also trying to use. And they compete with each other. They interfere. You're trying to do both of these things at once. You're trying to imagine the F, but then also use your actual vision. What it comes down to is there is some common element of your brain churning away that is active when you're using your normal vision and is also active when you're using your mental vision, your mental imagery. That's quite fascinating. Now, there's a lot of studies that branch out from here. We're just going to keep it simple today, but this has become an interesting and active field of study. Okay, so we've talked about this sort of shared resource issue of some mental imagery coming in and interfering with the same resources that we're using for actual vision. We can also talk about Shepard and Metzler. I like this one quite a lot. So, 1971, again, we're marching forward in the years. These are mental rotation studies. The question is, how do we actually take mental images and transform them? So here's an example to illustrate how this study works in general. Are these two objects the same object? The answer is yes. You can see that they have the same shape, right? But you kind of had to noodle that out for a second. You had to do some kind of process to figure out if they were the same or not. How about these two shapes? That's still a yes. They still have the sort of these are different than the first ones, but these are now This has a little 2-step block, has a 3-step block, and sort of a big L of 2 4s. Okay, great. How about this one? Are these the same? No, they are not the same. The 3 block on the end of this one goes a different direction. Somehow you're solving that. The question is not exactly down to the neurons of exactly how every one of them fires to solve this, but the question is, you can do this. You can solve these questions. What's the nature of that? And this study gets to the idea, a very interesting idea, that it's actually, you're doing some kind of internal simulation. You are doing something where so that the findings, I should clarify here, the further that the angle of rotation is away from the default image. So I have the F's here representing just like the 2D version of these 3D images. If the image is only rotated about 14 degrees, it takes you barely any time at all to solve, to figure out, right? Your mean is 1.5 seconds to figure this out in terms of your reaction time. Whereas if the F is rotated a whole lot more, say 214 degrees, well, that's going to take you several seconds to solve. What's going on? This big finding is about the idea that there's something very fascinating, that the time it takes to do this mental rotation task scales linearly with how much rotation you have to do. And it's an extremely strong effect. They tried all kinds of different things, and the primary thing that determined how long it takes to solve is how far you had to rotate it. What the heck? So, are we saying that I'm actually doing a physical simulation in my mind, in my brain? I'm actually solving every little frame? Well, there's room for interpretation, right? That this is not... This is only detecting the edges of this interesting phenomenon, right? We're not specifying all of the neurons and the activations and the networks and stuff. All we're saying is, this is possible, and this happens. So, we don't have the exact neurological evidence, but the questions that are raised are quite interesting. What is doing such a rotation, if anything at all? And then also, where am I keeping it? Where am I storing the information? Is it just distributed throughout the entire brain? Is it distributed throughout a certain little chunk of cortex that's dedicated to 3D image processing? Possible. Is it something else? Like, what we are still plumbing the depths of these questions even today. So this cracks a little bit of the imagery debate. There's a long-running fight, in a sense, a congenial academic fight about the degree to which mental imagery is actually used. It could just be a very robust, complex network of how different things interlock together, right? Are we actually just symbolically connecting things, and maybe we're solving the rotation task explicitly by way of some sort of mapping? We're saying, oh, here are the components of each of these shapes and all that. But that could be like the elephant map, but in much finer detail, and we're doing some kind of just symbolic processing to solve this stuff. But either way, whether or not we are using a purer form of imagery or a purer form of symbology, that's sort of a continuum question. The fact remains, we can do this. We can process visual information in these very robust ways, and they have these linear shapes to how long they take. So, in summary, the idea of mental imagery is that we can process on multiple layers here. We can process it at the symbolic layer, but we can also process at this non-symbolic layer. That we don't necessarily need strong symbols to process information. The light that comes into my eyes gives me a way to interact with the world. And if we think back to our goat friends, they're not doing a whole lot of complex symbol manipulation, but they are definitely making sense of their world in a sort of non-symbolic way. Vision. Vision shows that there's a thing out there that I need to be worried about, so I'm going to do a contact call. We can also conjure up some amount of mental imagery on our own, and it seems to use the same resources that actual, like, active vision does, at least some of them. And it seems we can simulate certain manipulations, certain physical manipulations in 3D space, similar to the actual physical process, as if we were grabbing and rotating this shape in our minds. And again, there's a lot of room for debate about how we're actually doing that. We're still working on it. Welcome to science. So that's the broad idea. Now, there's a very interesting exception that is still in extremely active research. And it's a medical condition called aphantasia. And it's only recently been discovered. The idea is that some people have no capacity for using mental imagery. They can still think just fine. And I would like to say to anybody in this crowd who is experiencing this now, it's okay. There is a whole lot of evidence that shows that this does not affect quality of life so much, but it may explain some interesting things in your life. So the idea is some people can't do this internal simulation. They can't summon up mental images, So if I tell you, imagine sitting in the sun on a beach, listening to the waves. Some people can come up with a form of that. Again, not perfect. I don't want everybody to think that in terms of like black and white here. Everyone has different degrees of this thing, but you can kind of hear the waves. You can kind of feel the sun on your skin. Kind of. You can imagine it. You can make use of the memory of it. It's hard to know if you have aphantasia because it's equated to being colorblind. You would go your whole life, you wouldn't even notice for sure. It's just that when people talk about being able to do this mental simulation stuff, it gets a little bit like, oh God, wait, you're not being metaphorical? This isn't a metaphor for picturing something? So we're gonna watch a little video about this just to explain it and show that it exists. Don't worry if you're feeling like, oh God, do I have this? It's possible you do. There is some active research on this even at Oswego, but it's a little bit on pause, I believe, for now, for obvious reasons. But we can talk about this. So anytime you want, send me a message. We can talk about it. But in any case, here is a short video on the phenomenon of aphantasia.
Thanks to CuriosityStream for supporting PBS Digital Studios. Okay, there's something I want you to visualize with your mind's eye. So if it helps, perhaps close your eyes.
In your mind, I want you to imagine the sky. It's really blue. And suddenly it becomes brighter. Then a rainbow appears. You turn your head and another rainbow appears. It's a double rainbow. It's so vivid and intense. Now, how clear is this mental image? Can you see each colour in the rainbow? Can you picture a bird flying in front of it? When some people are asked to picture something with their mind's eye, they just can't.
Hey Andy, it's Vanessa. How are you?
I'm quite swell. Yourself?
I'm well. Thank you so much.
Now, Andy believes he has aphantasia, a condition where you have little or no mental imagery. It's been referred to as blind imagination or having a blind mind's eye.
I asked Andy to visualize his breakfast table, and well, his brain uses different strategies to imagine these visual problems.
It's more akin to a word cloud, a long list of adjectives that describe the table. If you were to take me out of my kitchen and ask me to describe my dining room table, I could tell you things about my dining room table, but if I wasn't told the word was imagine, like image, I wouldn't use visual metaphors. When I imagine a coffee table, I'm more imagining concepts about coffee tables.
Now, I learned about aphantasia a few weeks ago when Andy commented on my last video.
I don't have any visual memory or imagination.
And people commenting on articles was exactly how this condition came to be studied in the first place.
Now, we've known that some people have a blind imagination since the 1880s, when Sir Francis Galton asked people to visualize things about their breakfast table. One of the subjects, actually Charles Darwin, said it was as distinct as if I had the photos before me. But a few people couldn't visualize the table at all. Fast forward to the early 2000s, when neurologists at the University of Exeter encountered patient MX, a Scottish man who lost his ability to visualise things after surgery. When MX was in an fMRI machine, researchers showed him a picture of then Prime Minister Tony Blair and asked questions like, does he have large ears? Well, yes. As expected, they saw normal activity in his visual areas. Next, they asked him to imagine Blair's face. They expected to see similar brain activity, but instead, many areas were active, including those used for semantic retrieval. MX was trying to imagine a face, but in a non-visual way, using words instead of images. When that research was published in 2010, Carl Zimmer wrote this article for Discover magazine, and emails started rolling in from people who experienced the same thing, some since birth. The blind imagination of this group of emailers was the focus of a new paper, published by the same researchers in 2015, who officially named this aphantasia. They found the majority of the group couldn't conjure up a mental image at will, but they still had flashes of vision, perhaps in dreams. Most said they had some trouble remembering past events, and most discovered their aphantasia in their teens or 20s.
Like, I'm a grown-up, and I didn't realize till recently that visualize, terms like mind's eye, I thought they were euphemisms, like maybe a quirk of the English language. It felt like not realizing that I was colorblind.
Right, wow.
From here, Carl Zimmer again wrote about this new paper. SciShow posted a video on it, and the researchers received close to 1,000 emails from people who just heard of aphantasia and believed they have it, similar to Andy. As the lead researcher put it, attesting it to the popular interest and relative obscurity of the fascinating variation of human experience. But why is the human experience so varied? Well, we don't know. But scientists are digging deeper into aphantasia using brain imaging.
The story of aphantasia shows us that we can all contribute to our understanding of how the brain works and how you work. And we're coming a little bit closer to finding out why some of us can visualize a double rainbow in the first
place. So that illustrates this, right? There is a strong difference among some people, and the more I've investigated this, the more I've uncovered things about this, and the more I've talked to people who research this, it's more about there's a wide array, there's a spectrum of your ability to imagine certain things, and some people only experience it for like smell or taste, or some people can't use, internal vision imagery. But that brings us to our final thought. Consider your own internal experience for each sense. Imagine a family member's exact facial features or the taste of a favorite food. How clear is it for you? Is this easy or difficult? Try to be honest with these questions, and don't panic. It varies for everyone. Just consider this may be an important individual difference between you and others' lived experience. All right, take care.